Hello, my name is Gemehl. I'm an energy technology student and I will be introducing to you in this video the MSFR and the Generation 4 of nuclear reactors. The Generation 4 International Forum is a cooperative international project which was set up to carry out research and development on the next generation of nuclear energy systems. The Generation 4 International Forum has 14 members around the world. The goal adopted by it provided the basis for identifying and selecting 6 nuclear energy systems for further development. The selected systems are based on a variety of reactor, energy conversion and fuel cycle technologies. Their designs include thermal and fast neutron spectrum reactors and closed and open fuel cycles. Through this video, we'll focus on one of these reactor designs, the Molten Salt Fast Reactor. The Molten Salt Fast Reactor, MSFR, is a further development of the graphite moderated molten salt breeder reactor originally designed at the Oak Ridge National Laboratory in the 1960s. Back then, an 8 megawatt thermal demonstration reactor with a thermal neutron spectrum using a molten salt formed by fluoride mix, which was used at high temperature and ambient pressure, operated during 4 years without any incident, from 1966 to 1969. The grand objective of the MSFR project is to prove the innovative safety concepts of the MSFR by advanced experimental and numerical techniques to deliver a breakthrough in nuclear safety and optimal waste management. The Molten Salt Fast Nuclear Reactor differs from other fast spectrum reactors by the liquid state of its fuel. This particularity leads to higher safety features and more flexibility. The molten salts, a fluoride salt mix in which fertile and fissile nuclear materials are dissolved, is fuel and heat transfer fluid at the same time. It circulates in a few seconds in a sealed circuit comprising a central primary vessel without moderator, the heart, where the fuel heats up, and 16 pumps and heat exchangers where the fuel transfers its heat to a secondary circuit. Like other fast reactors, the MSFR can consume plutonium from other reactors as fissile material. It can, however, also use thorium as a fertile material. The advantage of using a liquid fuel is that various fuel mixtures can be used varying in time. Furthermore, this kind of reactor possesses a strongly negative thermal feedback and void coefficients, which gives it a decisive safety advantage. First, the sustainability is assured for 2 reasons. The MSFR uses a closed cycle and is capable of consuming all fissile elements, those produced in the reactor itself and those produced in the other reactors. Secondly, thorium is more abundant in nature than uranium. The safety is a highlight of this concept compared to solid fuel reactors for 3 main reasons. The first one is the absence of reactivity reserve due to the possibility of continuously adjusting the liquid fuel composition without stopping the reactor. There is therefore no need of control devices which adjust the reactor core reactivity between 2 fuel reloadings. The second one is the auto stability of the reactor when the thermal demand changes, thanks to a strong expansion coefficient of the liquid salt. The third one is the possibility to drain the fuel salt by gravity into subcritical tanks located underneath the reactor core. As far as the subcritical tanks are passively cooled to remove the residual heat from the fuel, the system is in a safe state. The resistance in the proliferation of the thorium fuel cycle is recognized because of the production of 232 uranium associated with that of uranium-233. The uranium-232 has a radioactive decay chain leading to the emission of high-energy gamma rays. Such rays make the uranium derivation easily traceable and its manipulation very difficult. Of great social importance is the waste minimization. In fact, the only waste that can be minimized are the transuranic actinides. This indefinite recycling is facilitated by the recouped fuel. As MSFR is a very tolerant concept for transuranics, their incineration is possible and allows to significantly reduce the amount of actinides, thorium excluded, existing at the end of life of the reactor. Finally, a treatment of the fuel salt is needed to control its content of fertile and fissile elements and to reduce the concentration of various fission products. It is performed continuously during operation. One process is gas bubbling to extract the gaseous fission products and noble metals from the fuel salt. The MSFR appears to be a very promising system in the continued use of nuclear fission energy. It has promising characteristics in the fields of nuclear safety and sustainability, and it can also operate with the thorium fuel cycle, but can also consume the plutonium stockpiles from our current reactors. But a lot of research still needs to be done to develop this reactor line until commercial development.